fate of the universe is a fundamental question of cosmology. Its future evolution and the possibility of an end of time arouse enthusiasm, curiosity, but also fear in front of this fatality. Science puts on the path of our reflection small pebbles, fragments of theories, allowing to build a possible future of the universe. Dear traveler, good morning. Today we leave for an incredible temporal odyssey in search of answers on the future of our universe. How does its history end? Does it have an end? Only one way to find out. Take a ticket for this journey through the evolution of the solar system and the universe. But before leaving for a new adventure, think of liking the video and subscribing to the channel to not miss anything. Thank you, and have a nice trip. The era in which we are now is called the Stellar Era. This era did not wait for the birth of humankind, since it begins 100 million years after the Big Bang. In the near future, space exploration is developing. Humankind and its technologies manage to go further and further away, and to stay longer and longer in space, leading to the development of scientific knowledge. In 2051, one of the major achievements of astronautics since the success of the American lunar program is the landing of a crew on Mars. A technical and human challenge unlike the moon expedition, this mission required decades of preparation to solve all the difficulties it posed. The logistics of a trip lasting more than 2 years, with no way to go back, are not organized lightly. That year, in January, 4 astronauts landed on Mars after 9 months of launching from the United States to the Red Planet. At the end of a long 258-day cruise, the crew was transferred to a site prepared in advance to ensure the 500-day stay. The trip fulfills the dream of many great masters of science. In 70 years, Jupiter's famous large red spot has now completely disappeared. During the next 10,000 years, the structure of the solar system and the universe will remain stable. Only rare astronomical events will be appreciated. In about 4,700 years, the transit of Mercury will occur simultaneously with a solar eclipse. The latter occurs when the moon is in front of the sun. On this day, Mercury will also align with both stars. Deneb, a variable white supergiant star that became a pole star, is in the year 8,880 at its minimum angular distance from the North Celestial Pole. Deneb is the brightest star in the constellation Cygnus and the 19th brightest star in the sky. It forms with the stars Vega and Altair, the Summer Triangle, a star formation with intense radiation that you can easily see in the night sky in summer. The Gregorian calendar is out of step with the position of the sun in the sky by about 10 days. This solar calendar is based on the revolution of the Earth around the sun in order to determine an average time of the year in whole number of days. Thanks to him, humankind can follow the rhythm of the seasons. It will create a slight gap with the solar year, equivalent to a few days every 10,000 years, but this was considered quite tolerable on a human scale at the time it was adopted. A little before the 15th millennium, the precession of the equinoxes leads Vega of Lyra to become the polar star. On the axis of rotation of the Earth are 2 points of the sky, 2 celestial poles. The slow change of direction of the Earth's axis of rotation, due to the tidal forces that the Sun and the Moon exert on the equatorial bulge of the globe, is the precession of the equinoxes. The consequence of this is that the north celestial pole shifts on the vault of the sky along a small circle that it describes in 26,000 years. The star closest to the North Pole, and easily visible to the naked eye, is called the North Star by astronomers. Centuries after centuries, the North Pole continues its path on the celestial vault by approaching at times very bright stars. Vega of Lyra, one of the brightest stars in the sky, becomes the new North Star, located closest to the North Celestial Pole. In 13,000 years, halfway through a cycle of precession, which is the shift in the direction in which the stars are seen, the Earth's axis is tilted. Summer and winter then occur on opposite sides of the current Earth orbit. The seasons in the Northern Hemisphere, which already has more pronounced variations due to a larger percentage of land area, are more pronounced. Within 10,000 to 15,000 years, the red supergiant Antares explodes into a supernova. Antares is a gigantic star located 550 light-years from Earth, 10,000 times brighter than the Sun, and up to 15 times more massive. If positioned at the center of the solar system, Antares would be able to swallow the orbits of Mercury, Venus, Earth, and Mars. This red supergiant, being in the final stage of the evolution of a massive star, is slowly beginning its explosion into a supernova. This explosion, more than spectacular seen from the Earth, generates a phenomenal amount of light and ejects a lot of matter. However, it has no direct impact on the Earth because it is located much too far away. For a supernova to be dangerous, it would have to be located less than 25 light-years from the Earth. The Arecibo message, transmitted on November 16, 1974, reaches its destination, the Hercules cluster, within 25,000 years. This is the only radio message deliberately transmitted to such a distant region of the galaxy. Assuming a similar mode of communication is employed, a possible response would take this long to reach Earth. The Earth's orbital eccentricity reaches a minimum of 0.00236 within 27,000 years. The shape of the Earth's orbit is constantly decreasing, causing a progressive increase in the duration of winters and a decrease in the duration of summers in the Northern Hemisphere. The cold waves will be compensated by the reduction of the average radius of the orbit, increasing the temperatures in the Northern and Southern Hemispheres. The red dwarf star Ross 248 is an eruptive star that occasionally increases its brightness. Its trajectory brings it progressively closer to the Sun, so that in 36,000 years, it will be the closest star to the Sun at a distance of about 3,024 light-years. The transit of Uranus from Neptune The rarest of the transits among the 8 planets of the solar system will take place in the years 38,000. This transit takes place when Uranus is directly between the Sun and Neptune. It then takes the appearance of a tiny black disk moving slowly about the disk of the Sun. This transit lasts about 42 hours and is one of the most exceptional because of the long orbital period between the 2 planets of 172 years. The small apparent diameter of the Sun from Neptune and the smaller inclination of the 2 orbits with respect to themselves. In 40,000 years, Voyager 1 will pass off the star Gliese 445 at a distance of 1.6 light-years. At the same time, Voyager 2 will be 1.7 light-years away from the star Ross 248. After the distance of the red dwarf star Ross 248, Alpha Centauri becomes again the nearest stellar and planetary system to the Sun. Within 50,000 years, the Earth will be plunged into a new ice age, with most of its continents frozen over. The alternation of glacial and interglacial periods is linked to the concentration of greenhouse gases in the atmosphere, which modifies the temperature in its lower layers. Moreover, the astronomical position of the Earth in relation to the Sun has an impact on the amount of energy we receive. Despite the massive emission of greenhouse gases by humankind and global warming, the interglacial period, conferring a milder climate on the Earth, is coming to an end. The landscape then changes radically in appearance. The surface of the globe is covered by an icy steppe with low vegetation that grows slowly. Forests no longer exist. With an average temperature not exceeding 6 degrees Celsius or 42.8 degrees Fahrenheit, the cooling in some regions let appear thick layers of ice on the surface of the globe. Ice sheets are gradually forming on continental areas at high latitudes. The accumulation of ice on the continents causes a decrease in the level of the oceans and leads to the reappearance of part of the continental shelves. Under the weight of the ice, tectonic movements affect the ice-covered areas, and the world ocean circulation is radically transformed. Hudson Bay is reduced in depth by about 100 meters or 330 feet, and the Baltic Sea by 90 meters or 300 feet. Niagara Falls, although not the highest waterfall, is the most breathtaking for its height to water flow ratio. Not surprisingly, the resulting erosion completely undermined the 32 kilometers or 20 miles that separated them from Lake Erie and reached Buffalo. Niagara Falls is gone forever. In 50,000 years, due to the dissipation of energy by the tides, the speed of the Earth's rotation on itself is decreasing. The duration of a day increases by about 2 milliseconds per century. As the Moon moves away from the Earth, this lengthening of days becomes less and less rapid. Nevertheless, at this time, the length of the solar day reaches 86,401 seconds because of the lunar tidal forces, which slow down the rotation of the Earth. An additional second must then be added to the current clocks to finish a day. The Big Dipper, the Little Dipper, Cassiopeia, the Great Dog, or Orion do not form the drawings you have in mind today. The proper movement of the stars on the celestial sphere, resulting from their movement through the galaxy, makes most of the constellations unrecognizable. The modification of their position is mainly due to the precession of the equinoxes, which modifies the orientation of the axis of rotation of the Earth. Our view of the constellation is slowly changing as well as the reference point of the axis of rotation in the sky, the North Star. Located about 3,000 light-years from Earth, the hypergiant star VY Canis Majoris will end its life in a hypernova in 100,000 years. This explosion is one of the most powerful in the universe since the Big Bang, releasing the energy of more than 100 supernovas, which is equivalent to about 1,046 joules. Hypergiant stars are rare. Only a few monstrous stars of this category are present in our Milky Way, including VY Canis Majoris. Located in the constellation of the Great Dog, its diameter is equivalent to 10,000 to 15,000 times the distance of Earth to Sun. Hypergiants do not explode into supernovas. Their core collapses on itself until it forms a black hole, producing two very energetic jets of plasma emitted at the poles of rotation of the star at a speed such as the speed of light. Intense gamma rays are then emitted, explaining the origin of the gamma ray bursts. During the same period, events of tectonic origin continue to occur, and the surface of the Earth is constantly reshaped by tectonic uprisings, volcanic eruptions, but also by erosion. Vesuvius erupts dozens of times, and a dozen earthquakes of magnitude 8 and 9 take place along the San Andreas Fault. While the island of Hawaii had moved about 9 kilometers or 5.5 miles to the northwest a few thousand years ago, in 250,000 years, Loihi, the youngest volcano in the Hawaiian Emperor submarine chain, rises above the surface of the Pacific Ocean, creating a new volcanic island that will later attach to Hawaii. As predicted by the Wilson cycle, the movement of tectonic plates results in the birth of a supercontinent within 300,000 years. The plates on which the continents rest are eternally struggling to secure their place on the Earth's surface and are moving 30 to 600 millimeters per year. At first, Australia collides with Southeast Asia, Africa is pushed against southern Europe, and the Atlantic Ocean is even wider than today. The new supercontinent, Pangaea Proxima, begins to take shape from elements that were already stuck together in the past, forming a new single landmass. At the same time, Halley's Comet, the best known of all the comets, is breaking into fragments under the tidal forces of the planets. The cause is its nucleus, which is gradually eroded by its repeated passages near the Sun. By entering the inner solar system, the nucleus of the comet runs the risk of breaking up by brushing against the planet too closely. The part of the nucleus closer to the planet is more attracted than the part further away. The variation of the force of gravity, called tidal force, creates such difficulties that the body in question can succumb to it. The nucleus of the comet does not show a great internal cohesion and does not resist the tidal forces that will cause the planet from which it approaches. Halley's Comet breaks into many fragments before evaporating completely. Within 1 million years, the Earth will experience the eruption of the Yellowstone supervolcano, located in the United States, producing at least 2,300 cubic kilometers or 1,430 cubic miles of magma. This supereruption is a major catastrophe with a long-term global impact on the climate. Not only does Yellowstone generate a tsunami of lava, but also a massive cloud of ash, all scattered over several hundred kilometers. The sulfur dioxide, then released in large quantities, causes a cooling of the Earth's climate and a deterioration of the ozone layer. At the same time, in 1 million years, the red supergiant Betelgeuse will have exploded into a supernova. This explosion is easily visible in daylight. This red supergiant is located in the constellation of Orion. The largest known star after Antares, it radiates like more than 100,000 suns combined. As it explodes into a supernova, its brightness comparable to that of the Moon will illuminate the cosmos for several days. The signature of some neutrinos warns us in advance of its near deflagration, resulting in a burning beacon in the sky. Its brightness will gradually decrease until it disappears completely within 2 to 3 years. The energy released during the explosion is such that if Betelgeuse took the place of the Sun in the solar system, it would carry all the planets down to Jupiter. In 10 million years, the first steps of humankind on the Moon are now completely erased from the lunar surface. Mars has 2 moons, Phobos and Deimos. While the latter is moving away from the planet until it leaves its orbit, Phobos has been approaching it for thousands of years at a rate of 2 meters every 100 years under the effect of gravitational tidal forces. Within 40 million years, when it reaches a distance of 6,000 kilometers, or 3,700 miles from Mars, Phobos will exceed the Roche limit, the limit below which a satellite begins to break up under the action of tidal forces, exceeding the internal cohesion of the Moon. The internal structure of Phobos is very fragile. Its core is a mass of rock, hardly holding together. It is thus easily deformed. The forces of the tides, now so powerful, disintegrate Phobos. The biggest pieces will crash on Mars, forming new craters, but the smallest and the dust should stay in suspension, in orbit, and quickly spread around Mars to form a ring. Very narrow, but as dense as Saturn's rings, looking at the sky over Mars is something spectacular. Because of the northward movement along the San Andreas Fault, the California coast begins its subduction in the Aleutian Trough. The collision of Africa and Eurasia closes the Mediterranean basin and creates a Himalayan-like mountain range. In 100 million years, the famous rings of Mars will disappear. 100 million years later, it is the turn of Saturn's famous ring system to die out. The solar system completes a full revolution around the galactic center from its present position. Located at about 26,000 light-years from the galactic center, the Sun rotates around it at a speed of 240 kilometers per second, or 150 miles per second. It makes the turn in about 250 million years. It begins its 21st turn. All the terrestrial continents have now merged into a new supercontinent named Pangaea Proxima. As the tectonic plates collide and move apart, they create a new crust, leaving the old one to creep under the surface. In 300 million years, the two neutron stars of the binary system, PSR 1913, coalesce in a final gravitational wave chain, accompanied by a short gamma-ray burst. Rare are the binary systems of neutron stars. The general relativity imposed on two neutron stars rotating rapidly around each other causes periodic deformations of the very fabric of space. These are the gravitational waves. This loss of orbital energy causes the two stars to move closer to each other. Centuries after centuries, this approach leads to a coalescence, resulting in the emission of a powerful train of gravitational waves. The result of such an event is a black hole surrounded by a torus of debris, an ideal situation for the production of a gamma-ray burst, the most luminous event in the universe, in the electromagnetic wave domain. A gamma-ray burst, or huge supernova, occurs within 6,500 light-years of Earth in 500 to 600 million years. This is close enough to affect the ozone layer and possibly trigger a mass extinction of a significant proportion of Earth's living species. Due to tidal forces, the Moon has moved more than 20,000 kilometers away from the Earth. Even in the most favorable cases, the lunar disk can no longer completely cover that of the Sun. In 600 million years, all the eclipses are now of annular type. In its rotational movement on itself, the Earth drags the oceans and the tidal bulge that the Moon induces within this liquid mass. As the Earth rotates faster on itself than the Moon around the Earth, our satellite exerts on the bulge a restoring force that slows down the rotation of the globe. The lunar orbit increases to ensure the conservation of the angular momentum of the Earth-Moon system. In the long term, the two stars turn as fast on themselves as one around the other. From the Earth, you see the Moon only from one and the same hemisphere. This evolution of the Earth-Moon system leads to the end of total eclipses. At the same time, the Sun's increasing brightness begins to disrupt the carbonate-silicate cycle. Higher brightness increases weathering of surface rocks, trapping carbon dioxide in the soil as carbonate. As water evaporates from the Earth's surface, the rocks harden, causing plate tectonics to slow down, eventually stopping as the oceans completely evaporate. As there is less volcanism to recycle carbon into the Earth's atmosphere, carbon dioxide levels begin to fall. At this point, carbon dioxide levels drop to the point where C3 photosynthesis is no longer possible. Currently, the species using C3 photosynthesis represent 99% of the species. All plants that use it will die. The extinction of plant life is slowly taking place. The first plants to die out will be the herbaceous plants, followed by the deciduous forests, the evergreen broadleaf forests, and finally, the evergreen conifers. As the Earth begins to warm rapidly and carbon dioxide levels decline, plants, and by extension animals, may survive longer by developing alternative strategies, such as requiring less carbon dioxide for photosynthetic processes, becoming carnivorous, adapting to desiccation, or associating with fungi. The death of most plants will result in less oxygen in the atmosphere, allowing more DNA-damaging ultraviolet radiation to reach the surface. Rising temperatures will increase chemical reactions in the atmosphere, further lowering oxygen levels. Flying animals would be better off because of their ability to travel great distances in search of cooler temperatures. Many animals could be pushed to the poles or possibly underground. These creatures would become active during the polar night, dodging the days due to the intense heat and radiation. This is the earliest time for plate tectonics to finally stop, due to the gradual cooling of the Earth's core, which could potentially turn the Earth into a watery world. The Earth's atmosphere no longer contains enough carbon dioxide to allow photosynthesis. This mechanism, combining biochemical and biophysical reactions, allows plants, algae, and bacteria containing chlorophyll to synthesize organic molecules from the energy of the sun, water, minerals from the soil, and carbon from the air. Without CO2, photosynthesis cannot take place. Without plant life to recycle oxygen into the atmosphere, free oxygen and the ozone layer will disappear from the atmosphere, allowing intense levels of deadly UV light to reach the surface. However, some animal life may be able to survive in the oceans. At best, animal life could survive about 100 million years after the disappearance of plant life, the last animals being those that do not depend on living plants, such as termites, or those that live near hydrothermal vents, such as Riftia worms. To supply the energy needs of the sun, the nuclear fusion reactions that take place in its core must convert about 500 tons of hydrogen into helium every second. The main effect of this alchemy is the progressive reduction of particles, since it takes 4 hydrogen nuclei to obtain 1 helium nucleus. The more the density of particles decreases, the more gravity compresses the core. The more the temperature rises, the more the yield of the fusion cycles increases, and the more the sun releases energy. This is why the luminosity of the sun increases with the passing of time. Accompanied by an efficient greenhouse effect, the Earth has maintained a stable temperature, apart from a few periods of glaciation, which have allowed life to appear and evolve on its surface. Within 1 billion years, the solar luminosity increases by 10%, and the average temperature at the Earth's surface reaches 47 degrees Celsius, or 116 degrees Fahrenheit. The atmosphere becomes like a humid greenhouse, causing unstable evaporation from the oceans. Pockets of water are still present at the poles, allowing some refuges for life. The atmosphere is located with water vapor, which causes a runaway greenhouse effect, identical to that which would have occurred on Venus. The Earth becomes an arid desert where life has difficulties to maintain itself. However, at the same time, the radiation emitted by the sun will have increased, and its habitable zone will have moved outwards. The temperature on the surface of Mars is gradually rising. Carbon dioxide and water, currently frozen under the Martian soil, will be released into the atmosphere, creating a greenhouse effect. This will warm the planet until it reaches conditions comparable to those on Earth today, potentially providing a new island for life. A few million years later, eukaryotic life died out due to lack of carbon dioxide. Only prokaryotes remain. In 1.5 to 1.6 billion years, the increase in solar luminosity causes a shift in the habitable zone. As carbon dioxide increases in Mars' atmosphere, its surface temperature rises to levels comparable to Earth's during the Ice Age. Every second, the Sun emits a solar wind in the direction of our planet, corresponding to a flow of 1 million tons of protons and electrons. These particles are stopped on their trajectory by the Van Allen belts, the magnetic field of the Earth. Extending over 70,000 kilometers, or 43,500 miles, it is made up of the iron and nickel forming the Earth's core. The core is composed of a solid part, the seed, and a liquid layer 2,000 kilometers, or 1,250 miles thick. The uninterrupted stirring of the liquid metal layer causes the formation of the magnetic field. In 2.3 billion years, the outer layer of the Earth's core solidifies at a rate of 10,000 tons per second. The inner core continues to grow at its current rate of 1 millimeter per year. With the gradual disappearance of the liquid outer core, the seed occupies a large part of the space, and the Earth's magnetic field dies out. Deprived of its shield, the Earth is irradiated by the solar wind. In 2.8 billion years, the Earth's surface temperature, even at the poles, reaches an average of 147 degrees Celsius, or 296 degrees Fahrenheit. Life is reduced to single-cell colonies in isolated and scattered microenvironments, such as underground caves or high-altitude lakes, and dies out everywhere else. In 3 billion years, the median time for the Moon's distance from the Earth to be sufficient to attenuate its stabling effect on the tilt of the Earth's axis. The motion of the Earth's poles becomes chaotic. Earth's surface conditions are comparable to those on Venus today. In 3.5 billion years, the atmospheric pressure having reached 90 bars, it is now as difficult to walk on the Earth as it is to walk underwater at a depth of almost 1,000 meters, or 2,280 feet. The atmosphere is essentially composed of carbon dioxide. At the surface of the globe, the temperature reaches more than 450 degrees Celsius, or 842 degrees Fahrenheit. This oppressive heat causes the immediate evaporation of the smallest drop of water that could form in the atmosphere, thus explaining the non-existence of water on the surface. Thick clouds form and darken the Earth considerably, a very different physiognomy from the one you might have known. Life on this planet is a distant memory. 1 million years later, the moon Triton causes the rock limit of Neptune. The period of revolution of Triton is lower, which generates a slowing down of the moon by the giant planet because its orbit narrows by spiral. Triton then crosses the Roche limit and disintegrates under the effect of the tidal forces. The debris produced then gathers in a new ring system around Neptune, similar to that of Saturn in our modern times. In 4.5 billion years, the interactions between the Andromeda Galaxy, M31, and the Milky Way form a new galaxy, called Milkomeda. The Andromeda Galaxy, also named M31, is a spiral galaxy containing up to 1 trillion stars compared to 300 to 400 billion for the Milky Way. Made of gas and dust, it has a flattened disk shape and contains a bulge in its center. Initially located 2.55 million light-years away, the Andromeda Galaxy has always been the closest to the Milky Way. It has gradually approached a speed of 120 kilometers per second, or 75 miles per second. The meeting of the two galaxies does not seem at first to be a shock. Being so far away from each other, the stars will initially pass each other, without colliding head-on, before moving away. This apparent choreography will lead sometime later to a new approach, which is this time followed by a strong interaction between the two galaxies. Their orbits are strongly affected by the anarchy of gravitational forces in place during the interpenetration of the galaxies. This encounter leads, after 2 billion years, to the birth of a gigantic system weakly provided with interstellar gas, a new galaxy, Milkomeda. Unlike its two parents, this new galaxy is elliptical in shape, and the stars it contains are scattered in a sphere. The Milky Way and M31 no longer exist. The new galaxy sees the appearance of a new outbreak of stars, but the little remaining gas being quickly consumed, the formation of stars stops, and the galaxy will slowly die out as its new stars die. In 5 billion years, the Sun leaves its main sequence and begins its transformation into a red giant after having exhausted the reserves of hydrogen in its core. The energy released during the fusion of hydrogen nuclei in the core of the Sun feeds the frenetic agitation of sharp particles that exert a powerful pressure towards the outside. It is thanks to this pressure that the Sun swells and does not collapse under its own weight. Until now, this balance was maintained. But now, at 5 billion years, it is no longer the case. Even if the Sun is still full of hydrogen nuclei, it has almost none left in its core. The fusion of hydrogen produces helium, which has heavier and denser nuclei than hydrogen. It is in the core of the Sun that the temperature is the highest, about 15 million degrees Celsius, or 27 million degrees Fahrenheit. The fusion of hydrogen into helium requires 10 million degrees Celsius, or 18 million degrees Fahrenheit. On the other hand, the fusion of helium requires a temperature of about 100 million degrees Celsius, or 180 million degrees Fahrenheit. The Sun does not approach this threshold at any point, so as helium replaces hydrogen in the core, the fuel supply for fusion will decrease. The pressure from energy production will decline, and gravity will prevail, causing the Sun to implode. As its gigantic mass collapses in on itself, the temperature of the Sun will rise dramatically. Despite this pressure and the extreme temperature, helium fusion is still not possible, and the hydrogen then starts a second phase of fusion within a thin layer around the helium core. The fusion of hydrogen occurs at an inordinate rate. The thrust is then much more intense than before. The Sun will swell to colossal proportions, reaching more than 100 million kilometers in diameter, or 62 million miles in diameter. It becomes a red giant. Obviously, the planets of the solar system will directly undergo this change. The Sun, of decreased mass, exerts a gravitational attraction, less which allows the planets to migrate on more distant orbits. Do the planets only go far enough to win the race against the increasing diameter of the Sun? Mercury loses the race, swallowed by the Sun and briefly vaporized. Mars, orbiting farther away, makes it through the race unscathed. Venus is lucky. The Sun stops swelling, just before reaching its new orbit, and at the same time, the Earth is also spared. The conditions are nevertheless fundamentally different. The Earth and Mars are in synchronous rotation with the Sun. The average temperature now reaches several thousand degrees. The oceans are vaporized, the mountains melt, the atmosphere is ejected, and the surface is covered by streams of lava. What does a sunrise look like from the Earth today? Instead of a nice, warm, and cheerful yellow disk, a gigantic red circle, reminiscent of blood, takes its place, slowly rising above the horizon. Once the sun has risen, it exudes its heat, which is felt as if you were putting your head in an oven, heated to the maximum. Mars will soon experience the same fate as Earth. The atmosphere is starting to warm up. Potential life forms on this planet will not withstand more than 1 billion more years. From now on, 2 new orbits take place in the habitable zone of our solar system, the orbits of Jupiter and Saturn. Although neither planet is suitable for life, either Jupiter, with water in its clouds, or Saturn, being completely made of gas, their respective moons could become suitable places for the appearance of a primitive form of life once their temperatures have risen. Thus, simple organisms could see life on the surface of Enceladus or Titan, the moons of Saturn, or Europa, the moons of Jupiter. A little less than 3 billion years later, the Sun reaches the top of the branch of red giants with a maximum radius 256 times greater than its current radius. Venus is totally destroyed. The future of the Earth is very uncertain. Despite the passage of time and its totally unrecognizable surface, the Earth is still present. However, the history of the Sun, in its form of red giant, does not stop there. As the hydrogen nuclei continue to fuse around the core, more helium will flow into the center, and the temperature will rise even higher. The cycle will be fed. The fusion of hydrogen in the shell around the core accelerates, and the flood of helium to the center intensifies. This phase will last 500 million years before the core finally reaches the temperature necessary for helium fusion, a process that produces carbon and oxygen. This transition from hydrogen to helium fusion is marked by a spectacular eruption, during which the Sun contracts to a more constant subgiant structure. This new equilibrium is short-lived because 100 million years later, in the same way that helium had displaced hydrogen, the carbon and oxygen nuclei chase helium from the core towards the neighboring layers. The combination of oxygen and carbon now requires higher temperatures, at least 600 million degrees Celsius. This time, the core will never reach the required temperature to restart the nuclear reactions. Its mass is not high enough to reach temperatures that would allow the fusion of carbon and hydrogen nuclei into heavier and more complex elements. The burning of the helium shell continues, and the core continues to contract until the Pauli exclusion principle stops the implosion. The quantum mechanism acts as a repulsion. It is as if the electrons refuse to be compressed further, causing the Sun to stop contracting. The outer layers continue to expand and cool before being dispersed in the cosmos. All that remains is a ball of carbon and oxygen of staggering density, called a white dwarf. It will continue to shine for a few billion years. The fusion reactions will stop because the temperature is not high enough anymore. the thermal energy of the Sun will be slowly dissipated into space, leaving a dark, cold globe. The Sun, with a mass equal to 54.05% of its current mass, becomes a white dwarf composed of carbon and oxygen. Our Sun is now dead. Its heart is exposed. Its power of attraction on orbiting bodies, such as planets, comets, and asteroids, will have weakened because of its loss of mass in the previous stages. All the orbits of the remaining planets will expand. The orbit of the Earth is now twice as far away as the orbit we know today. All planets will become dark, icy, and completely devoid of life. They will continue to orbit their star, their speed being reduced due to the increased distance to the Sun and its reduced gravity. More than 4 billion years later, the white dwarf Sun has cooled to a temperature of 2,000 degrees Celsius, or 3,630 degrees Fahrenheit. Its luminosity falls below 3 billionths of its current level. Its heat is no longer measurable. It is now invisible to the human eye, as its radiation is weak and drowned in that of the cosmological background. The Sun passes from the structure of white dwarf to that of black dwarf. In the case where the density of dark energy increases with time, the expansion of the universe accelerates until all structures, from clusters of galaxies to nucleons, are torn apart. In order to protect ourselves into the scenario of the end of the universe, we must take into account the properties of dark energy, this enigmatic entity, and only ingredient that seems to accelerate the expansion of the universe, whose slowdown seemed inevitable. The universe would be filled with a form of dark energy, described as phantom energy, whose density increases with the expansion. Strengthening over time, this energy would reach an infinite density in an infinite time. Stronger than all other forms of energy that contribute to the cohesion of the structures of the universe, the phantom energy would tear everything apart. Clusters of galaxies, planets, molecules, atoms. The entire universe ends, stretched by an expansion, more and more violent, 35 billion years after its formation, in a big rip. The expansion of the universe leads all galaxies outside the local group to cross the limit of the cosmological horizon and to disappear beyond the observable universe. This phenomenon, comparable to a swelling of space, leads celestial objects to move irreparably away from each other. Within 100 billion years, many galaxies will be chased against their will into this mysterious part of the cosmos. From this unobservable universe, the photons emitted will never reach us, since the regions of deep space are moving away from us faster than the speed of light. In 106 billion years, the universe could be driven to its end in a big crunch, a big crack, a kind of Big Bang in reverse. The future of the universe is torn between the attractive effect of gravity and the evolution in time of the repulsive effect of dark energy. The dark energy could dilute with time and become an attractive force. Gravity would then take over, and the Big Bang would occur again, but in reverse. Like a big crunch, the first thing to happen would be the disintegration of galaxies, the evaporation of stars, the breaking up of atoms, the disintegration of nuclei, the formation of black holes, sucking in everything around them, and the merging into a single black hole, enclosing the whole universe. Only a singularity remains, hot and dense, canceling space and time. 50 billion years later, the cosmic microwave background cools down, making it undetectable with current technologies. This electromagnetic radiation is observed throughout the universe and strikes almost uniformly in all directions. Usually measured at a temperature of minus 270.45 degrees Celsius or minus 454.8 degrees Fahrenheit, it now reaches the temperature of minus 272.85 degrees Celsius or minus 459 degrees Fahrenheit. In 450 billion years, the 50 or so galaxies of the local group merge into a single galaxy. After the Milky Way merged with the Great Andromeda Nebula in Melkomeda, the latter began to slowly swallow up all the other members of the local group, one after the other, until it formed a single, giant elliptical galaxy. When the merger between the Milky Way and M31 started, many small galaxies of the local group became under the gravitational grip of the two large spirals. The Milky Way traps the dwarf elliptical galaxy of Sagittarius, half broken by tidal forces. The Andromeda Galaxy, which is more massive, retains for its part a dozen dwarf galaxies, two elliptical of a larger size. The conditions are thus favorable for the merger of the Milky Way and Andromeda to lead to the coalescence of the local group into a single, giant elliptical galaxy. This process fits directly into the cold dark matter model, by which the formulation of large structures is explained by successive mergers of smaller entities. The total luminosity of the resulting galaxy starts to decline by 800 billion years. Red dwarf stars with a mass less than 0.25 solar masses, the most massive ones evolving into red giants, move into blue dwarfs. The luminosity of stars increases as they age, but this luminosity requires faster energy production to maintain its hydrostatic balance. Some red dwarfs increase their surface temperature by increasing their radiative rate and thus become rather blue in color. At the same time, the temperature of the universe reaches the Gibbons-Hawking threshold, the lowest temperature that can exist, the absolute zero, and it's minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. In 1,000 billion years, the stars begin to cease to be born in the galaxies, those not comprising any more cloud of gas necessary to their formation. The energy reserves necessary for stellar nucleosynthesis are exhausted, and the nucleus of stars will gradually turn into iron, the most stable atomic structure. The lightest elements will release energy during fusion, while the heaviest elements will release it during fission. The limit between the elements stabilizing by fusion or fission takes place at the level of iron 56. Within a star, it is thus towards the iron that the matter will tend. The expansion of the universe, assuming a constant density of dark energy, multiplies the wavelength of the cosmological background by 1029. All galaxies have crossed the cosmic horizon scale, making this evidence of the Big Bang undetectable. The visible universe contains fewer and fewer galaxies. Except for the stars of the Milky Way, even the stars of the local group have now passed beyond the cosmic horizon. For billions of light years, the sky remains pitch black, lightly illuminated by the last glimmers of darkened and almost cold white dwarf stars. Only replicas of barren and desert planets and stable interstellar dust clouds are still present. Within 10,000 billion years, all the stars in the galaxy will turn into dark bodies, black dwarfs, neutron stars, or black holes. Despite some remnants of interstellar gas, they are now too heavy and too diluted to tend to the formation of new stars. Even if the interstellar medium still collects some matter released by massive stars, or during episodes of fusion between galaxies, these contributions are insufficient to form new stars. The density of dark energy being constant, the forces of nature slowly lead the expanding universe into a cooling. The end of the birth of stars and galaxies occurs in 100,000 billion years. The stellar era ends, and the era of degeneration begins. Hydrogen is no longer available to form new stars. Those that exist exhaust their fuel and die out. The iron atoms turn into neutrons. The electrons orbiting outside the nucleus will combine with the protons, releasing neutrinos. The latter will carry another 30% of the energy of decay of matter. The largest stars will turn into black holes in cases where the pressure exerted by neutrons to counteract gravity is not strong enough. Thus, after 1 million billion years, all the stars in the universe have exhausted their fuel. The longest-lasting stars, the red dwarfs, have a lifespan close to 10,000 billion years. Only they still light up the sky slightly, with a surface temperature below minus 3,725 degrees Celsius, or 6,737 degrees Fahrenheit. Their low mass allows them to maintain a fairly low core temperature, thus implying a slow-motion fusion where energy is transferred to the surface by convection. The core then feeds the nuclear fusion cycles of the star with all the available hydrogen, giving it a slightly longer life. From then on, the only remaining objects of stellar mass are stellar remnants, white dwarfs, neutron stars, black holes. Brown dwarfs also remain. The remains of stars dominate the universe. The gravity of passing stars will have completely stripped the dead sun of its remaining planets. This point marks the end of the solar system. Although the sun and planets may survive, the solar system as we understand it will cease to exist. All brown dwarfs and stellar remnants are ejected from galaxies within 100 billion years. When two objects pass close to each other, they exchange energy. After repeated encounters, low-mass objects can obtain enough energy to be ejected from their galaxy. All bodies are disrupted by gravitation by 1 million billion years later. Planets begin to escape from their star systems and wander under the influence of gravitational fields. most stars are expelled from the galaxies. The tiny part of those that remain are compressed in the center of the galaxy until they form a single large star under the force of gravity. In parallel with the increase of its density, its core eventually collapses, forming a galactic black hole with a mass equal to that of 100 billion sun. The very dense gravitational repulsion forces at the heart of these galaxies give rise to strong explosions of matter and radiation. The majority of galaxies are expelled and become galactic black holes in 1 billion years. What remains becomes intergalactic black holes. Eventually, hypermassive black holes persist within superclusters of galaxies, surrounded by an accretion disk that spreads energy. The grand unification theories describe the matter-antimatter asymmetry and mention that the proton is not eternal. Thus, at the end of this period, all bodies will dissociate into electrons, positrons, neutrinos, and photons. All the stellar fuel is spent. The universe has become extremely dark since the last red dwarfs have reached the end of their long evolution. Although the galaxies have left their ultramassive black holes in place, lacking gas to fuel the accretion process, they do not cause any radiation. All kinds of stellar cores are scattered after the evaporation of galaxies. There are residues of massive stars, like black holes or neutron stars, and many cooled white dwarfs. When two of them get close to the point of collision, the supernova that occurs causes a flash that illuminates the universe with a dazzling glow. Other encounters from stars by which the mixture of carbon and helium pierces the darkness. All these stars that can still activate, and just like the aborted stars, planets and other small bodies of rock or ice are made of nucleons. The nucleons, composed of 3 quarks stuck together by a strong interaction, are considered stable, but can still disintegrate within 1 billion years. A proton decays into a positron and a neutral pion, an unstable particle that rapidly splits into 2 gamma photons. Also, black holes are the only stars that remain beyond 10,000 billion years, or 10 to the 40th power years, in a universe flooded with particles from the decay of protons. Thus, a new era begins, the era of black holes. In 10 to the 43rd power years, all the nucleons of the observable universe decay, if the half-life of the proton takes its smallest possible value. Assuming that the Big Bang underwent an inflation, and that the same process that allowed matter to predominate over antimatter leads the proton to decay. If this is the case, the era of black holes begins where these are the last celestial objects. Assuming that the proton does not decay, all rigid objects, such as rocks, rearrange their atoms and molecules by tunneling within 10 to the 65th power years. At this timescale, all matter is liquid. According to Hawking's theory, although undergoing a very slow process, black holes eventually evaporate, letting the only remaining energy in the universe escape. At 10 to the 92nd power years, the universe is almost a thing of the past, containing only subatomic particles and low-energy photons. Black holes are the last remaining elements that continue to feed on the last remaining stars in the galaxy. Black holes, reaching the end of time, are of the order of trillions of solar mass. The time required for a supermassive black hole with a mass of 1,013 solar masses to evaporate by Hawking radiation is estimated at 10 to the 106 power years. This process marks the end of the black hole era. After this time, if the proton decays, the universe enters the dark era, in which all physical objects have decayed into subatomic particles, gradually reaching their final energy state. But if the proton does not disintegrate, the story continues. All nucleons in the observable universe have decayed by one of the many possible mechanisms in modern particle physics, such as the non-conservation process of the higher-order baryon, virtual black holes. While until now iron was only formed at very high temperatures in supernovas under the tunneling effect, quantum physics predicts that all atoms can be transformed into iron, even at low temperatures. Under the effect of Pyknon nuclear fusion reactions, a black dwarf star made of ashes, remnants of hydrogen and cold helium, is transformed into a ball of iron in a period of 10 to the 1,500 power years. This period is called the Iron Age. The most massive black dwarfs explode in supernova until there is nothing left in the universe. Meanwhile, the neutron age marks the transformation of iron nuclei into neutrons, an even more stable particle. The stars turn into black holes under the effect of their own mass. In 10 to the 1,500 power years, if the proton does not decay, all baryons have either fused to form iron-56 or decayed to iron-56 from a higher mass element. All iron stars collapse via a quantum tunnel into neutron stars or black holes, assuming no proton decay. Black holes, even the most massive ones, are not eternal and do not survive the Hawking radiation mechanism. A mixture of quantum mechanics and general relativity, it is as if a quantum fluctuation of the vacuum causes a particle and its antiparticle to appear just at the horizon of a black hole, and that one of the two disappears inside while the other escapes. This type of radiation thus contributes to slowly reduce the mass of the black hole, which can initially reach up to 100 billion solar masses, until its complete evaporation in a cloud of gamma photons. The more massive the black hole will be, the slower the evaporation will be. Like a gigantic fireworks finale, the darkness of the sky will be illuminated by the intense flashes of black hole evaporation. Once rid of these and any other object composed of nucleons, the universe is nothing more than an immense, empty, and cold space. If the dark energy has finally burned out and the rapid expansion of the universe has slowed down, it is possible that these particles will accumulate into larger black holes, which will radiate even more slowly and remain for longer. However, if the energy is maintained, the particles will be scattered faster and faster by the accelerated expansion, and will therefore meet only very rarely, if at all. These conditions are similar to those that prevail just after the Big Bang, but in this late universe, the assemblies of particles become improbable because of the acceleration of the expansion and the dispersion of the elements. This cosmic dust will just drift in the vacuum. This period would be assimilated to the end of time, but events that seem improbable today because of the considerably long durations continue to punctuate the void. Years later, around this vast period, the quantum tunneling effect in any isolated part of the universe could generate new inflationary effects, leading to new Big Bangs, giving birth to new universes. Modern physics is accustomed to considering all kinds of invisible substances that permeate space. It seems that in a truly empty space, in the conventional sense of the term, the particles have no mass at all. Space must therefore not be empty, and the particular substance it contains must have the right properties to give the particles the masses we observe. This is the Higgs theory. In concrete terms, when two particles collide at high speed, the shock disturbs the surrounding field, which is itself impregnated with an invisible substance called the Higgs field. Just as a ping-pong ball thrown in the air feels like a drag force, this disturbance can be enough to eject a tiny part of the field, which manifests itself as a new particle called the Higgs boson, like an offspring of the vacuum. In our journey through the cosmic timeline, it could be that at some point the value of the Higgs field changes. Just as the drag of the ping-pong ball would change with the density of the air, the mass of the fundamental particles would change if the value of the Higgs field changed. Atoms and molecules depend intimately on the properties of the elementary particles that constitute them. If the masses of these particles change, their behavior also changes. The probabilities that the Higgs field will evolve in the future are amplified because of the infinitely large time spans involved when the end of the universe is evoked. The physical mechanism studying this question is the tunnel effect. To better understand this theory, you can imagine a champagne flute inside which you place a marble in its bottom. The marble, being retained on all sides by the walls of the glass, and its energy being insufficient to climb them, it remains immobile at the bottom of the flute. The same thing happens with an electron, which remains most of the time where it was placed. Thanks to maneuvers explained by quantum mechanics, the electron disappears and rematerializes outside its trap. The more constraining the trap is, the lower the chances that the electron has to escape. In the real world, there is no such thing as a completely zero probability. The electron will therefore, sooner or later, succeed in escaping. This phenomenon also applies to fields that penetrate barriers and change their value. Thus applied to the Higgs field, the tunneling effect could determine the long-term fate of the universe. The current value of the Higgs field is 246. It has been stable for billions of years. Quantum considerations allow the Higgs field to cross its barriers and to observe a variation of its value only at certain places. At this place, a bit like the ball would fall if it materialized outside the walls of the champagne flute. the value of the Higgs field would know a lower energy, and would push the neighboring regions to operate the same transition. The latter, by domino effect, would enter an expansion. Consequently, the masses of elementary particles are modified in the part where the field is modified, while they remain the same outside. The border between these two regions moving at the speed of light, it is impossible to feel in any way what is formed outside. The empty space itself remains unstable and can be made to evolve in a very distant timescale until causing a cataclysmic end of the universe. It is statistically possible that the value of the Higgs field will fall in a few billion years to a minimum of its different potential energy. It could become much stronger and gain mass, which would have radical consequences. Galaxies, stars, planets, and atoms could no longer interact as they do today. A small bubble could be created punctually with another potential minimum in the Higgs field, expanding at the speed of light. The Higgs field of our universe will slowly tilt towards the new potential minimum, creating what looks like an alternative universe inside our own universe, which will itself be swallowed up. And if the speed of expansion is the same as the speed of light, it will be impossible to perceive this bubble. What a dark fate for our universe. Everything is based on theories and speculations. The only thing that can be said today is that not everyone who is watching this video will witness it.